Esters are found extensively in nature. The aroma and flavors of various fruits are in a large part attributed to esters, and esters are widely used as flavoring agents in the food industry. Um, we saw in section 210 that the ester group is found in fats and oils, as well in a lot of waxes. In chapters 22 and 23, we're going to discuss how esters tend to react. Now, we'll do this in organic chemistry too. But here, what we're going to ask is, how can esters be synthesized? Now, one method is to treat carboxylic acid group. So that's that carboxylic acid functional group, which I'm going to abbreviate as Ca, with diazomethane. Now, diazomethane is CH2N2. And what happens here is that the acidic hydrogen is replaced by a CH3 to produce a methyl ester, right? And so when we talk about the acidic hydrogen, it's the hydrogen on the carboxylic acid. That's the acidic hydrogen. And then it is replaced with that CH3 group, and that comes from the CH2 N2. Notice as well that we're going to produce nitrogen gas. Now, let's look at that mechanism. All right, I had to stop the screencast for just a moment, so if there was a pause there, you have not missed anything. So here we are. We're going to jump into this diazomethane mechanism. This mechanism consists of a proton transfer followed by a nucleophilic substitution. Now, I could draw those double rings, and you absolutely will be expected on an exam to draw an entire molecule. But what I'm going to do right now is just shorten those rings to an R group. And then show you the functional group so we can really look at that functionality. Now, let's look at the diazomethane. That diazomethane, that's a terrible carbon. Let me go back. It's got a negative group on it. Now, that does have a resonance structure, so it is particularly stable. I did not leave myself enough room, don't be me, but I'm going to show the resonance structure kind of out this way. Right, and so there's some kind of fun brackets there. Okay, those would be up and down brackets. But we do have resonance structures here. Now, when you start a mechanism, you always want to kind of think about what's electron rich and then what's electron poor. Electron poor things a lot of times are acidic, right? And so here, what we have is an electron poor acidic hydrogen. So that's electron poor. It's an acidic hydrogen. And then we want to come over here and find what's electron rich. And so this carbon has a negative charge on it, and so it's electron rich. And it's got electrons, right? We see those. And we remember from our mechanism training that the electrons, right, flow from things that are electron rich to electron poor. There's an attraction there. So what happens is these electrons are going to come out and they're going to attack this acidic hydrogen. When they do that, the electrons that make up the oxygen-hydrogen bond are going to go here back on that oxygen. And so that's a generic, just kind of proton transfer. Mechanism. Now, this a lot of times is called a carboxylate ion or anion. It's a carboxylic acid group that has been deprotonated. The proton has been removed. And at this stage, what we're going to see is now that oxygen is really electron rich, and if we follow our arrow here, now we have CH3 in, 1, 2, 3, in, okay? And so while this guy here is very electron rich, right? This carbon here is very electron poor. There's a positive charge here, right? And so it's kind of sucking the electron density off, and so it becomes very electron poor. And so the arrow starts at things that are electron rich. These electrons are going to come over. They're going to attack that carbon. Those electrons are going to go onto the nitrogen. That's an SN2 reaction, or SN2 mechanistic step. And now we have formed our ester group, and we have formed nitrogen gas. And this nitrogen gas, that is an excellent leaving group, okay? And so we talk about it being an excellent leaving group, and it's an excellent leaving group for two reasons. The first reason is N2 is extremely stable, right? It's one of the most inert compounds known. And two, it's a gas, so it bubbles out of the solution as it's formed, and that permanently removes it from the reaction mixture, so it drives the reaction to completion. So this reaction itself is very favorable. We don't have a reverse reaction in this case. So this is a really great way to synthesize esters. Now, we are going to kind of change gears and talk about amines for a moment. Amines have a characteristic carbon-nitrogen single bond. There are several different types of amines that are shown here. Remember, the R here is a carbon. And these amines are classified according to the number of alkyl groups that are attached to the nitrogen. So a primary amine only has one alkyl group, a secondary amine has two, a tertiary amine has three alkyl groups, and then we have a quaternary ammonium ion. This is a nitrogen with four alkyl groups attached to it and carrying a positive charge. That's very similar to the ammonium ion that you had to memorize when you're memorizing your polyatomic ions in general chemistry. Now, amines are abundant in nature. We can look at some examples of these. You can see some examples here. The characteristic functional group appears in amino acids as well as neurotransmitters like histamine. The functional group also appears in synthetic dyes like methyl orange, which is shown here. And it's common in pharmaceutical drugs like pseudoepinephrine, which is shown here, which is a nasal decongestant that's marketed as Sudafed. So if you've taken Sudafed, that is the medicine that you're taking. Now, some quaternary ammonia compounds have cleansing properties and are found in consumer products like shampoos and detergents, while others are lethal to microbes and are used as disinfectants. Quaternary ammonia ions can be used as phase transfer catalysts. Now, a phase transfer catalyst just facilitates the reaction of reagents that aren't soluble in the same solvent, so they can serve as synthetic intermediates. And we're going to look at an example of this in the Hofmann elimination reaction. So, amines can be produced from alkyl halides. So I'm going to draw a generic alkyl halide here. I'm going to use bromine as my halogen, and then the R group is the alkyl part. And you react an alkyl halide with ammonia. Ammonia is simply NH3 here. And this will undergo an SN2 reaction where the you see that the bromine is electron rich, which makes the R group partially positive or electron poor, right? And then the nitrogen here is very electron rich. And so negatives and positives like each other. The electrons here come out and attack this R group, which is partially positive, and those electrons go back on the bromine. Okay, so when we do this, okay, we've formed an ammonium ion, so we need to put the plus charge here, okay? And then what can happen again is this can go through a proton transfer with another molecule of ammonia. Remember, there's lots of molecules of ammonia floating around. If we could imagine a reaction flask, right? And so this is going to come in and steal a proton. When it steals a proton, those electrons go back on the nitrogen. And so now we have an R group with an NH2 with 2 electrons there, and then the ammonium ion here, and we have synthesized a primary amine. Okay. When we look at this, this is called an alkylation reaction. And so in an alkylation, a hydrogen atom is replaced by an alkyl group, okay? The ammonia here, notice, is uncharged, and it's a moderately strong nucleophile. It's also weakly basic, so that causes it to be quite reactive as well. Now, although amines can be produced by these kinds of alkylation reactions, there is a major problem that can occur because the amine product is also nucleophilic. So this primary amine that we've made here, right, that sucker right there is also very nucleophilic. And that means that amine product, when it encounters another molecule of an alkyl halide, it can go through a second alkylation. Now remember, when we do these reactions on paper, a lot of times we forget, but we've got lots of these molecules floating around, and so they can continue to go on and react. Don't forget that. So, like I mentioned before, that primary amine is a nucleophile. There's that primary amine. We have more of that alkyl halide floating around, and so it can undergo an SN2 reaction, where those electrons go there, and those electrons go there. And now, right, this can go through the exact same reaction, an SN2 and a proton transfer. Right? And now we have a secondary amine. But the problem here is that secondary amine is also nucleophilic, and so that secondary amine can now react to form a tertiary amine, right? And then the tertiary amine can react to form the quaternary amine. And so in our reaction, the simple reaction that we're trying to do, now we have 4 products. When really we're just looking for 1 product. So to help ensure that the alkyl halide reacts with NH3 instead of an amine product, and therefore we minimize those subsequent alkylations, the reaction can be run with an excess of NH3. Okay, so as shown here in equation 1056, right? Now, what that does, and that's what you're seeing here is the 3 equivalents here. When we talk about it being in excess, all this does is minimize these subsequent alkylations. So you do this and you get 57% this primary amine, right? But we're still seeing some pretty substantial amounts of undesired product in the mixture, right? The secondary amine, the tertiary amine, and then trace amounts of that quaternary amine. And so alkylation isn't usually a very effective way to synthesize amines, especially primary amines from alkyl halides. Although alkylation is generally a poor method of synthesizing amines, so if you're like me, you're like, well, if it's a poor method, Dr. Pierce, why did you teach it to us? Well, it turns out it's a pretty effective method for synthesizing quaternary ammonium ions here, right? So if we look at equation 1057, which is this equation here, basically you can take an alkyl halide, you add NH3 excess, and the quaternary ammonia ion can be the major product, right? 8 hours at elevated temperatures. And so that's what this synthesis tends to be used for, is for this quaternary ammonium synthesis. Now, when we talk about amines, amines can also be used to synthesize things like double bonds. Now, this becomes very important. We're not there yet, but in organic chemistry 2, you're going to see where double bonds are incredibly versatile reactants. They can undergo a lot of reactions and give you a lot of reactivity. So we're going to look at this reaction here. What you see is that but-1-ene is produced when butane 2-amine is treated with excess iota methane, which is that CH3I, and then treated with silver oxide and then heated. This is an example of a Hofmann elimination reaction. The formation of a carbon-carbon bond does strongly suggest that an elimination reaction's occurred where the leaving group contains the nitrogen atom, okay? Now, there are two aspects of the Hofmann elimination that we need to reconcile, okay? The first is that we know that amino groups are terrible leaving groups and don't participate as substrates in elimination reactions. And the major product here is a terminal alkene, which is the less stable or the less alkyl substituted. And that means it's less stable because it's less alkyl substituted of the two possible elimination products. So another way of saying this is that, hey, this is the anti-Zaitsev product, or also known as, so another synonym here is the Hofmann product. So in the Hofmann reaction, this is called the Hofmann product, and it's the anti-Zaitsev elimination. So let's look at the mechanism to see how this reaction occurs and how we can resolve those two issues. So when we look at the Hofmann elimination reaction, I'm going to start out with my friendly, I'm going to draw my bonds really well. I'm not going to draw lazy bonds. I'm going to start out with the NH2 here. Okay. And this is going to undergo an SN2 reaction. So what's going to happen is that these electrons are going to come up. They're going to attack this partially positive carbon because that iodine's electron withdrawing. And those electrons are going to go right there on the iodine. So it undergoes an SN2 reaction. When it does that, it forms a quaternary amine. So we're going to have a positive charge there. Okay. The next step is a proton transfer step. Where these electrons are going to come in, they're going to steal that proton, they're going to drag it back. These electrons go right here on the nitrogen. We follow our arrows, and so we see that the product that's formed is the amine there, right? And what's going to happen is this, and you can draw these out. This is going to go through 2 more alkylations, and I want you to practice drawing 2 more alkylations here. On the test, you would need to draw these alkylations out, okay? So, but I want you to take this opportunity and practice drawing those alkylations. So after 2 more alkylations, that's just SN2 proton transfer, SN2 proton transfer. The product that you would get is your quaternary ammonia salt. With a positive charge there, okay? Now, the next reaction that comes in is Ag2O, okay? Silver oxide here is the base. So when it's added, right, it just replaces I minus with OH minus. So basically it's going, well, basically it's going to make this basic, okay? And so then what can happen here is, with our quaternary amine, and I wrote that backwards and that's not correct. We need to make sure our carbons there is attached. We're going to have a positive charge there. And we are going to have some acidic hydrogens here. And so we have our acidic hydrogen here, and we have an acidic hydrogen there. Now, we have a strong base, which is OH minus. Now, so deprotonation can either occur at C1, which is right here, or C3, so carbon 1 or carbon 3. Now, the major product here is 1-butene, so what happens is OH minus has to deprotonate here at this first carbon. Now, this is particularly odd because, as we learned in chapter 9, a small strong base like OH minus typically leads to a more highly substituted elimination product, which would be the outcome of deprotonation at C3. That, of course, is not what we see here, and we'll explain this is regioselectivity, and we'll explain that on the next slide. But basically, it happens because there's a lot of steric. I wanted to show that there's a lot of steric bulk here. All right, so that's a really big kind of bulky group. These are all single bonds. They're all rotating around. Basically, it's just harder to get to that hydrogen on C3. It's a lot easier to get to that hydrogen. So it comes in through an E2 reaction, and it steals that hydrogen, and those electrons go right there, and it bumps off this NH2 group. And so it's NH2 group. NCH3 group, and forms this guy. Right there. So let's look at some kind of visualize that steric bulk and what we're talking about. So when we look at this steric bulk, it helps us if we look at this with a Newman projection. And so we are looking down, we've got it numbered 1, 2, 3, 4, they're your carbons. We are looking down the 2 and 3 bond here. All right, so I'm sure you heard all sorts of commotion in the background, so I had to pause the screencast. I'm restarting the screencast. So you haven't missed much of anything, but I'm kind of going to restart just to make sure. So the regioselectivity, as we mentioned, of the Hoffmann elimination reaction can be explained by the steric bulk of the amine leaving group. And so I want you to remember from section 8 or chapter 8 that E2 reactions are favored when the proton and the leaving group that are eliminated are anti each other. Okay? And so when we look here, we notice that it's difficult for a proton at C3 to be oriented anti the leaving group, because when either the C3, so this is a Newman projection, we're looking down the 2 and the second and the third carbon, because when either the C3 proton is anti, the leaving group and the C4 methyl are gouged to each other, right? So that causes steric strain on that C3 kind of proton there. And the molecule instead prefers to have all the methyl groups anti and both C3 protons gouged to the leaving group, which is shown here. Okay. And so that means that elimination involving a proton at the third carbon is really unlikely, right? So it is not favored. However, as shown here, right, the hydrogen atom on carbon 1, so this is carbon 1, can be anti, and remember anti just means kind of on the opposite side here to the leaving group, and it doesn't cause any excessive steric strain. And so in this case, the E2 reaction is favored. And so that's one of the reasons we see that Hofmann elimination product or the anti-Zaitsev product. Now, so we've seen kind of how to synthesize double bonds using elimination reactions, and those of course are alkenes, but we also can synthesize or generate alkynes using elimination reactions. Now, alkynes, I just want to remind you, have a characteristic carbon-carbon triple bond. Some naturally occurring alkynes are bioactive. This tends to be not seen as frequently, though. So this molecule here is found in carrots and acts as a natural pesticide. So you can see the triple bonds there. These triple bonds can also be found in some pharmaceutical drugs. And this was formerly marketed as an oral contraceptive. The molecule that makes up the poison and the poison dart frogs also has a triple bond, which is kind of interesting. Now, alkynes have a widespread use in industry and synthesis. So honestly, alkynes aren't found in nature as much as alkenes are, but we do use them in industry and synthesis. So for example, remember from chapter 9 that the terminal alkyne, okay, so this is a terminal alkyne. Terminal alkyne just means it's going to be at the end of the beginning of the molecule. If the alkyne is anywhere inside the molecule, it's an internal alkyne. Now, this is weakly acidic. So shown there in red, that's weakly acidic, and it can be deprotonated using a strong base, like sodium hydride shown there. Now, that results in an alkylide ion, and that's an anion, and that is a strong nucleophile. And so that's got that negative charge. We know this is partially negative, that's partially positive. There's an attraction between things that are negative and positive, right? So this undergoes an SN2 reaction, right? And we can produce a new carbon-carbon bond. This is a big deal. Basically, in organic chemistry, being able to grow larger molecules from smaller molecules is a way that we can synthesize large biomolecules or large pharmaceuticals. And we don't have a lot of reactions that can help us do this. So being able to grow a carbon chain is really important. Now, we are going to see in chapters 12 and 13, right when we come back from Christmas break and we enter organic 2, that this carbon triple bond can undergo functional group conversions to produce other type of compounds like alkenes, ketones, and aldehydes. And so for all of these reasons, it's important to be able to synthesize alkynes. So very, very useful in synthesis. One way to synthesize an alkyne is by carrying out an E2 elimination reaction, which you can see here in equation 1061. Now, in this case, the leaving group is in the vinylic position. Now, this is where I have a southern accent, and it's very hard for me to say that word. It's like vinyl, so vinylic. And so I have a really, really hard time saying it. When we talk about something that's in the vinylic position, it's attached to a carbon-carbon double bond, right? So what we're talking about here is if you have something that's attached to a carbon-carbon double bond, right there, that's the vinylic position. I want you to notice, just like other E2 reactions we've looked at, the proton and the leaving group are not on the same carbon. They're on adjacent carbons, okay? So notice the proton and the leaving group are on adjacent carbons, okay? Because the leaving group's attached to an sp2 hybridized carbon, the vinylic substrates are really quite resistant to nucleophilic substitution and elimination reactions. Under normal conditions, even a strong base like a hydroxide ion generally doesn't facilitate this type of reaction. As a result, these reactions are carried out under more extreme conditions, generally at a temperature of around 200 degrees. Okay, so we've got some pretty extreme conditions here. Now, these are some examples of vinylic halides. You can see these are vinylic chlorides. We find the double bond. There's the chloride off of the double bond. There's the chloride off of the double bond. If a much stronger base is used, so before we jump into that, this is KOH. So this is providing that OH minus, that hydroxide ion, with heat, so that 200 degrees, right? And it has to go overnight. You can see we can turn where there's this vinylic chloride here, we can turn that into the triple bond there, right? But if you use a much stronger base like NaH or NaNH2, right? These are much stronger bases, right? Then the elimination reaction can take place without the extreme heat, okay? And so stronger base, you don't have to use as much heat. This can take place at room temperature overnight. That's really, really helpful. People generally don't love to have things at 200 degrees and then leave the building, right? So you don't want to also have to stay in the building to watch it overnight. So this is really advantageous here. And so you can see here that we've taken this and turned this into a triple bond there. So when a strong base like that sodium hydride or NaNH2 is used and the elimination product is a terminal alkene, like here, right, we typically add an acid after, and that allows the elimination to finish. This is a lot of times called an acid workup step, right, where you see number 2 here. This is, they've already got it labeled for you perfectly. It's an acid workup. So let's look at the mechanism to see why the acid workup is important for this particular mechanism. So There is our vanillic halide. It's a bromide there. And we are going to add the sodium hydride, and that just gives us a hydride ion that looks like that. Okay. And it's going to come in and it's going to steal the proton on the carbon adjacent to where the leaving group is, and that bromine's the leaving group. So it is not going to steal this proton next door. Go next door. When that occurs, these electrons come down here, and this is the leaving group there. Okay. And so now we have our triple bond here, and then it's going to go out to a hydrogen. Okay. So I'm going to show that. There's a carbon, carbon, and then a hydrogen bond. Okay. Now, the other thing that we also have is hydrogen gas. Okay. And then we've got some Br minus rolling around. Now, this is an E2 reaction, and this is going to undergo a proton transfer pretty quickly because we still have that hydride running around, right? Just because it's reacted once doesn't mean another molecule can come in and react again. So another molecule is going to come in and it's going to steal that proton. And when it steals that proton, these electrons go right back on that carbon. Okay. And so now you've got this guy here. Okay. And so this can, the reaction with that NaH stops here. So reaction with the NaH stops here. Now, with the acid workup, and so this is the acid workup step, you've added NH4Cl. Now that dissociates and forms NH4 plus and Cl minus. And so, just like this. And so these electrons come down and they steal that proton, and those electrons go on the nitrogen, and that's a proton transfer step. Right? And so now we have that. So the acid workup is really necessary for us to replenish that proton there on the terminal carbon, right? And we recover the desired uncharged products. We don't have a charged product here. Now, elimination reactions that produce alkynes are particularly useful, as I mentioned, when we begin with a dihalide, such as 1,1-dichloropentane, which is shown here, or 1,2-dibromo-1-phenylethane. Notice that here we have 3 equivalents of NaNH2, which the Na is the spectator ion, so that's really NH2 minus, right? And that converts the dihalide into an alkyne. And the way that does that is the first 2 equivalents bring about separate E2 reactions. So we have 2 E2 reactions with those first 2, and then the third equivalent of the base deprotonates that acidic proton on the newly formed terminal alkyne. And then, of course, the acid workup step will help us replenish that proton. So this here, that is showing you the acid workup. okay, which is just a generic H2O, okay, because in this situation, H2O is more acidic than the reactants, okay. Now, notice in equation, the bottom equation here, 1067, we do not require an acid workup. There's no 1 and 2 there. And the reason is because the OH is not a strong enough base to favor deprotonation of the terminal alkyne that forms. So no acid workup because that OH minus is not a strong enough base to deprotonate the terminal alkyne that's formed. So here ends for us chapter 10. In our next screencast, we are going to go into organic synthesis 2, which is chapter 11, and we are going to start to look at designing multi-step syntheses.